Okay, so what we're going to look at is how do we calculate the frequency for a signal generator to be injected to the RPX to create sidebands that are harmonics of a resonant frequency of based on calculating it by the size of something. So if we look at 100 nanometers, which is 0.1 microns, I believe, in meters. Okay, we have this many meters. 0.0000001 meters is 100 nanometers. So if we go to a frequency wavelength calculator, and we know that the wavelength is 0.0000001 meters, we're going to go to meters. Okay, using meters. This is the frequency in hertz. That's fast. Okay, so if we take that and we enter that into a spreadsheet, and obviously this is too fast for a signal generator to be output or the RPX or anything like that. We're going to have to take a harmonic, so we're going to divide it by 2, 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 and so forth. So the wavelength formula is speed of light over the frequency is going to give the wavelength, and so if we have the wavelength, then inversely we can, calculate what the frequency is going to be, and that's what we just did. So now we're going to open up a spreadsheet. We're going to divide this frequency in half as many times as possible to get down to a frequency, which is going to be a harmonic of this, that's close to the 3 megahertz range. So we're going to do that step next. Okay, so what we have here is I did the same calculation for 160 nanometers. So I'm just looking at, if this is for 100 nanometers, this is the frequency for 100 nanometers, and this is the frequency for 160 nanometers. You can see it's quite a bit slower. That's because that's almost twice the size. And so the frequency is going to be reduced quite a bit since there are less repetitions of that frequency per second over the same distance in space. Okay, so what this calculation is just taking this frequency, dividing by half, and then this one is dividing that by half, and so forth, till we go all the way down to a frequency that is close to 3.1 megahertz. So we're down here at the, let's see, this is, okay, we have no header. So the 31st harmonic, which is quite a bit out there, is 2.79 megahertz. And for the 160 nanometers, it's about 3.5 megahertz. So what we're going to do is we're going to look at the difference between the frequencies, which is 3.1 megahertz, and then we're going to subtract this, and we have a difference of 308,000 almost. Okay, so if we just round this off to an even number, let's say 307,964, and we do the same thing with this, we're taking this frequency, 3.5 megahertz, and we're subtracting 3.1 megahertz because this is a higher number. We're just looking at the difference. We don't want negative numbers. The sidebands are going to create the addition of and subtraction of anyway. So what we're looking at is 390 kilohertz. So we're looking at roughly about 300,000 hertz to 400,000 hertz. And if we divide those by half, we got 150, then 200, or 75 and 100,000, 37,500 and 50,000, 18,750 and 25,000. So what this means is in the signal generator, if you sweep from 18,750 to 25,000, you would be getting the sidebands that are going to be harmonics of the resonant frequency for these ultra high frequencies up here, which are resonant frequencies for something that would be, for example, 100 nanometers or up to 160 nanometers in size. Okay, so in Rife's day, he's only going to have a audio signal generator, which may be sweeping from 0 up to 40, 50,000 hertz is going to be typical. Okay, and in his day, he didn't easily have a signal generator that went 300 to 400,000 hertz. You're going to get stronger sidebands, I believe, the closer you are to this fundamental. Okay, and so, but what we're going to do is we're going to take these numbers. I already printed them out. We're going to put them into the signal generator, and we're going to sweep, and we're going to see if indeed we are hitting the difference here of 2.79 megahertz and 3.49 megahertz. And if we are, then we know that we're hitting the harmonics, the 30th harmonic of the frequency for 160 nanometers, and a 31st harmonic of a frequency hitting 100 nanometers. Okay, and if we see that these two frequencies, 2.79 megahertz and 3.49 megahertz, are being hit at peaks of sidebands, you know, close to the 3.1 megahertz fundamental, then we have successfully calculated the resonant frequency for being able to sweep where the sidebands are going to hit 100 nanometers up to 160 nanometers. Okay, so we're going to go to the shop, check it out on the spectrum analyzer, and verify. That'll be the next step. Okay, what I'm going to do real quick is I'm going to turn this signal generator on with the RPX. Both are powered from the 12-volt battery. And we're going to go into the normal Bedini protocol sweep mode, which is 150 kilohertz, or 100 hertz to 150 kilohertz. Sweeping linear, everything 50-50. Okay, so now that it's sweeping, and if you're not operating a Rife machine by sweeping the audio range and mixing with the fundamental, you basically have a fake Rife machine. That's pretty much indisputable. So what we're going to do is I'm going to set up this spectrum analyzer so that we can monitor the frequency range that this is going to be operating in, the exact frequency range as Rife's. So what I'm going to do is I'm going to hit frequency. We're going to look at the fundamental of 3.1 megahertz. Okay, we got that in the middle. So if I turn the signal generator off, we can see that we just have the fundamental right there of 3.1 megahertz. Okay, I'm going to make the span about 1 megahertz. That's how far we're zooming in. I'm going to turn the signal generator back on, and we're going to start sweeping, and you can see how it's creating the sidebands. Okay, these sidebands are hitting frequencies which are even harmonics of the exact Rife frequencies, sweeping automatically through them, so it's irrelevant what any particular frequency is because it hits them all, and that's the whole point. That's what Hoyland developed with Rife, and that was their ultimate evolution. And if you do not have that function on your Rife machine, you do not have a Rife machine. Okay, so what we're going to do is, so earlier in the video, what you could see, if I can zoom in on this, is that what we're looking at is the 2.79 megahertz, and the 3.49 megahertz is for 100 up to 160 nanometers. Using that frequency, dividing it in half over and over until you find a even number harmonic, divided by 2, and so forth. This is like the 31st, and this is like the 30th harmonic. Interesting, it's 3.1 megahertz and it's the 31st harmonic. But in any case, these are close to the fundamental, 2.7 megahertz and 3.49 megahertz. So exactly, it's 307,965 kilohertz is the difference between the fundamental and that harmonic. And you get the difference, and that's the frequency you put into a signal generator to create the sideband, which is the harmonic of that frequency, which is a going to hit the which is a harmonic of the actual frequency that you're looking for something that size. So for example, we have 307,965.1617. We're going to round that down to 307,964, and we might as well just bring it down a little bit in the range to 300 kilohertz and 400 kilohertz. You can divide those in half and use harmonics, divide by 2, divide by 2, divide by 2 to get into a signal generator range of what like Rife would be using. But if you're actually closer up here, to it, then you're going to have sidebands that are going to be closer to the fundamental and are going to be quite a bit stronger. And so I'll demonstrate that. I'll demonstrate it with, let's say, maybe, let me look in the signal generator. So I've programmed a few protocols here. Excuse the messy bench here, been busy lately. Okay, so what I'm going to do is I'm going to hit System, I'm going to load, let's see, let's go to System, okay, load 1, load mod. Okay, so those are the actual frequencies themselves, 307 up to 390. Okay, so those are the exact numbers. So let's go ahead and just sweep that and see what happens. And if we go ahead and sweep, hit OK. So what we're doing is we're sweeping the frequencies from the low one, which is the difference between a harmonic of the 100 nanometers and the difference of the fundamental. And if none of this makes any sense to you, go watch my video on how to calculate the right frequencies with the sidebands. Okay, so what I'm going to do is I'm going to focus on the spectrum analyzer up here. Okay, so what I'm going to do is I'm going to hit a marker, and marker number 1 is 3.1 megahertz, and you can see that little number 1 right there is tracking 3.1 megahertz fundamental. Okay, and so the frequency to use to create a sideband, which is an even harmonic, the 31st harmonic of the frequency that coincides with the 100 nanometer wavelength, is, we're going to go to another marker number 2. We're going to type in 2.792034838. It's not going to get that accurate, but what it's going to do is it's going to be pretty close, 2.791666. Okay, so what we see is we got that number 2 right there, and every time that number 2 hits up on a peak, it's getting that exact range, and when it drifts off, that means that frequency is sweeping through a different range. Now what we're going to do is we're going to put a marker on the high one, which is 390,043. Okay, so let's see. So that's going to be marker number 3, which is going to be 3.4900435548. Doesn't have to be that accurate again. Okay, so we got number 3 hitting up on a peak on here. And so what's happening is every 10 seconds it's going to sweep from the frequency, which is a harmonic, of the frequency coinciding with 100 nanometers up to 160 nanometers. So we can see this is in the lower sideband, this is in the upper sideband, lower on the lower side of the fundamental and upper on the upper side of the fundamental. Okay, and so to make maybe see it a little bit easier, I'm going to lower the sweep frequency, or the time, to about 1 second. So you can see, okay, maybe that's a little bit too fast. Let's go every 4 seconds. So you can see they're kind of out of phase because it's obviously going from low to high. And so number 2, we see a peak up way up on that sideband right there, which means it has pretty good amplitude. And then we see this number 3 pop up, and it's hitting up here for 160 nanometers. But wherever that 2 is and that number 3 is, it's actually hitting all the frequency ranges in between. Okay, it's just peaking at the low and the high, and it's interesting that the fundamental of 3.1 megahertz just happens to be right in the very middle of that, pretty much even right between them. It's pretty interesting. It's like it was meant to be. Okay, so you can see where these are in relation to the fundamental. Now what I'm going to do is I'm going to change the program on the signal generator to sweep using harmonics of the sweep range of which are the exact differences between these frequencies, between the fundamental and the harmonic. And so what I'm going to do is we're going to use these ones down here, which Rife could have had access to easily with the audio signal generator. And the great thing about this is that Bedini's protocol is to sweep from 100 hertz to 150 kilohertz. It's automatically going to hit these, but we're just going to see if we can actually get stronger peaks closer to the fundamental using higher numbers coming out of the signal generator that we're sweeping. And Rife didn't easily have that available in his day. We do these days, so might as well use them if that's what we're trying to learn from. Okay, so I'm going to go to in the signal generator. Okay, so what I'm going to do here is I'm going to show you Okay, so what I'm going to show you right here is that the low frequency is set for 18,750 hertz, well within the audio range, up to 25,000 hertz. Okay, and so those are roughly divisible by 2 by 2 by 2 of the actual exact frequency. So we're just going to see where these frequencies are in range, and I'm going to set it to sweep every say 4 seconds like the last demo. Okay, and I'm going to hit the OK button to start to sweep when we're looking at the spectrum analyzer. So let's go back up here, look at the spectrum analyzer here. Okay, and we still got our marker set for 2, 3, 1. I'm going to hit OK, and now we're sweeping. And what we see is a clear difference that when we use harmonics that are further away, whatever frequency, divide by 2, divide by 2, divide by 2 to be within the capability of your signal generator, that when we go down that many times, we basically have this first kind of peak here, second kind of peak here, and you see how far away it is with these different so-called peaks. But also what we're looking at is that the amplitude is really, really low. Before, our amplitude was up here, and now it's way down here, which means exactly like I'm saying, you're getting way stronger results by using frequencies that you're injecting that get you a sideband that has got a higher amplitude closer to the fundamental. And what I'm going to do is I'm going to load the other frequency where it's sweeping from 307 kilohertz to 390 kilohertz, and you can see a huge difference that we get these peaks way up here, which are very, very strong, almost as very close to the strength of the fundamental itself. Okay, so let's see as we sweep. Okay, so that's about 3 seconds, so you can easily see. But what you're seeing is we're able to get a higher amplitude. And if we went up even more and went from 600, if we actually doubled those numbers, then we could see maybe even stronger. But the point is with your Velamin signal generators, the FieldTech or the Coolertron, I have videos on the Vril website showing you how to program the sweep mode for the Coolertron and the FieldTech. The Velamin, you're going to have to look on YouTube or read the instruction book that you can find online. And if you swept from 300,000 to 400,000, just to make it easy, you're going to get that entire range. And so this is basically showing you how to look at the size of something, say 100 to 160 nanometers. We know what the frequency is. We divide that over and over by 2 by 2 by 2 until you get a number which is close to the fundamental. Then you subtract them to see the difference, and that difference is going to be the number that the signal generator must mix with the fundamental to create a sideband for that frequency. Again, if you don't really understand what's going on here with the sideband calculations, you need to see my video on the Vril website, vril.io, mouse over products. then click on the RPX link, and at the top of that page, one of those videos is on calculating the sidebands for the right frequencies, and I would recommend watching that, then come back and watch this one, and it'll make sense to you. So again, to sweep in a more narrow range to for something from 100 to 160 nanometer wavelength, for example, this is how you do it.